In this recording, we're going to apply theories from the counting principle, permutations, and combinations to count some fairly complicated situations. Okay. Hopefully you have your companion packet that has this title and has these questions on it. I'd like to back up though and start with even something more simple. Let's just look at how many ways we can arrange the letters in the word cat, because that's something we certainly can wrap our head around. So there's 3 letters, and one way is to make a sample space. So I'd like you on the side of your paper to list out all the different ways you can arrange the letters of the word cat. And order matters because we're talking about arrangement. Play the recording when you're ready. Okay, so hopefully you wrote down as many ways as possible. This is what a sample space would look like. Okay, those are the 6 ways, and there are 6 different ways. Another way would be with a tree diagram. In a tree diagram, we say, well, you could start with a C. If you use the C, you've got an A and a T left. If you use the A, well, there's only a T. If you use the T, there's only an A. So setting things up in a tree diagram leads us to the same answer, 6 ways. Show the whole tree here. Finally, an alternative way to do it would be to say, hey, there's basically 3 spots for the 3 letters. When I'm choosing the first one, I've got 3 choices. Once I've used one of those choices, there's only 2 left for the second one. And obviously the third one just falls into place. 3 times 2 times 1 is 6. Another way to say that would be 6 factorial. 3 times 2 times 1, if you remember, 6 factorial, back up, 3 factorial, getting carried away here, 3 factorial is the same as 6. Okay, and as these numbers get large, we certainly want to rely on some of our counting theory. Next, I'd like to get your companion packet, and I'd like you to read through that first example involving the cafeteria. Underline the important stuff, and play the recording when you're ready. Okay, so hopefully you recognized here, in terms of how many spots there are to fill, that there's really 3. So in each case, we want to say how many spots are there to fill, and what are their names. So there's 3 different decisions a person has to make: a dinner, a salad, and an entree. Okay? And then you want to think about, okay, how many possibilities are there in each one of those choices? And from the reading, you can see that there's 5, there's 4, there's 3 different possibilities. As you saw with the word cat, we simply just multiply those. That's the counting principle. 5 times 4 times 3, we have 60 different choices. Okay? I'd like you to read through the next example on your own and figure out how many spots there are, and to the best of your ability try to put labels on those, and then play the recording. Okay, so hopefully you had a chance to underline the important stuff. One of the key words is without replacement there. That means these Scrabble pieces, if you can think of these letters as Scrabble pieces, we're not going to put them back once they've been used. It says there's a 4-letter code, so let's just set up 4 spots. 1, 2, 3, 4. And there's particular criteria that they're using. It says it has to begin with 2 vowels. All right, so we're going to call that a vowel and a vowel. And it also specifies that a vowel could be a Y. And it doesn't say anything about the other letters. So what I'd like you to think about is this could be any. This one could be any. All right. Now we just have to look at the numbers, see what we're given. So the first slot needs to be a vowel, and I only see 4 of them. So fill that slot with 4 numbers. Once we've chosen, for example, say we pulled out the A, now there's only 3 vowels to choose from. So that's 3. Now, this slot could be filled by any of the letters, but you've already pulled out 2 of them. So for example, say I pulled out the O and the A. Now there's 7 letters left. So 7. And once you've used, say, the L, or whatever it was, there's 6 left. Okay? Multiply all those, and you've got 504 codes. Okay? That's the counting principle, in essence. Next, we're going to look at permutations. Okay? So you've got a definition here on your sheet. Permutations is an arrangement. The keyword arrangement. Other keyword already underlined for you, order. Things that are in order. Runners in a race, songs in a playlist, offices that have a particular designation like vice president, president, etc. like that. Arrangement of books, things like that. Order matters. So I'd like you to read through number 3, play with the recording when you've had a chance to underline it. Okay, so in this one, we're going to think about is I basically got 1, 2, 3 spots, first, second, and third place. Order matters to these people, to these runners. They care if they get the gold, silver, bronze. Okay, first, second, and third. There's 10 runners eligible for the first place. Once one of those is finished, there's 9 that could possibly finish second, and there's 8 that could finish third. So if you do a quick multiplication on that, you'll get 720 ways. Now, we're going to introduce new notation here. Permutation notation. Okay? An alternative way to do it is to do it this way. We're going to use this P notation. And we're going to say it's an arrangement of 10 items or things, 3 at a time. Okay, so I'd like you to write that in your note. An arrangement of 10 items, 3 at a time. Okay? That's what this is saying. That's what that P notation is saying. Once you've got that written down, pull out your graphing calculator if you have one. Okay, so if you have a graphing calculator, use that. If you don't, just watch along. We're going to enter a 10 on the home screen. There's 10 items to choose from to arrange. We're going to go to Math, scroll to the right to Probability, and choose choice 2, NPR. Okay, an arrangement of 10 items, 3 at a time, comes out to be 720. That's exactly what we figured out by multiplying 10 times 9 times 8. Here's an example for you to try on your own. I'd like you to read through example 4, then play the recording when you've written something down. Okay, in this example, we again have permutations. It's an order question. Okay, whether or not Darla cares about the order, her songs will be in a particular order on her player. So, we could think of this in terms of permutation notation because it asks us to do that. So that would be an arrangement of 12 items. We're going to use all of them. So 12 items, 12 at a time. That's our permutation notation. Check. Factorial. Well, we'll probably do that third. Okay, 12 items, 12 at a time means there's 12 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 that need to be filled. 12 songs for the first spot, 11, and so on, all the way down to 1. Okay. Now you can see how tedious this is and why we like factorials, especially if there were as many songs as you probably have on your iPod. Okay. There would be an extraordinary amount of numbers to multiply, and the number of arrangements would be quite high. Okay, so you put all that into your calculator as 12 factorial. Okay, on your calculator it's 12, and then under Math, go to the right to Probability. It's the 4th choice down. 12 factorial. It's a lot easier than typing in all those numbers. Let's say it's 479,001,600. So, once again, we've expressed the number in terms of an integer, which is right here. And I always put a label on there. It says up here how many different orders. Let's say it's orders. That's the number we got from our calculator. Here's the notation that we put into the actually, we could have put in the calculator. We didn't. We used this notation, 12 factorial. It's the same thing. So, let's get into a very interesting and typical question that's asked that involves repeated letters. Okay? We're going to do parts 5 and 7 together. You're going to do number 6 on your own as your check for understanding. Okay? So, I'm going to work through the fairly complicated one here. I'll do that second. We'll start with the simple one. How many letters in the word clock? Well, if I'm looking for 5-letter arrangements, I'm going to first think about, well, if there were no repeats, it would just be 5 factorial, right? 5 times 4 times 3 times 2 times 1, just like with cat. However, unlike with cat, there's really no way for me to tell this C from this C. They're indistinguishable. So I have to take out the 2 repeated C's because there's 2 factorial ways of arranging the number of repeated C's. So what I'd like you to write down here is 2 repeated C's. Okay? And then we just do 5 factorial divided by 2 factorial. It turns out it's 60 words. Okay, you could multiply it all out, or you could use your calculator if you have one. All right, let's get into number 7. 7 is complicated. So, how many 11-letter words can be created with the letters in the word Mississippi? Well, if there were no repeats, remember, it would just be 11 factorial. It would be 11 times 10 times 9, all the way down to 1. However, there's lots of repeats. This is like a classic question here, Mississippi. We have to account for all the different letters that are repeated. We've got a 4 factorial for all the I's. Okay, I'll just label that. There's 4 I's. We have 4 factorial for the S's. And finally, we've got the P's. So I've got 2 factorial for the P's. Okay? So you can put that all into your calculator. 11 factorial in a mini fraction over 4 factorial times 4 factorial times 2 factorial. That all works out to be 34,650 words. Okay? Number 6 is for you to do on your own. Bring that one to class. Thanks for watching.